Hi guys. So in this tutorial, we're going to cover inequalities. And what I'd like to do is start the topic from scratch and build our way up to the content that is going to be tested on your final exam. But what I'll also do is I'll put timestamps in the video. So that way, wherever you all think you need to start from, you could start from there. So the first thing that we need to talk about is what actually is an inequality. So we know what an equality is or an equation is. We've seen those before, so maybe we've seen something that looks like this. And basically, what this says is that the value that I have on the left-hand side is the same as the value that I have on the right-hand side. But what if I wanted to compare two quantities that are not necessarily equal, right? So let's say I have two boxes. I have box A and I have box B. And both of these boxes have cookies in them, right? So let's say box A has 5 cookies and box B has 3 cookies. Then I could compare the number of cookies in these boxes and I could say, okay, box A has more cookies than box B. So what I just did is I assigned a value to these unknowns A and B, and then I compared them and I made a conclusion. I said, okay, A is greater than B. So if I wanted to formalize that in more mathematical terms, let's say we have two unknown quantities, X and Y. And I'm going to compare these two quantities. Then I could say one of maybe four things. I could say, okay, the value of X is more than or greater than the value of Y. Or in other words, there are more cookies in X than there are in Y. I could say the value of X is less than the value of Y, right? So this time Y is greater than X. The next thing I could say is, okay, maybe X is greater than, or it could be equal to the value of Y, right? Because these are unknown values. So maybe the value of X is the same as Y, or maybe it's more than Y. That's greater than or equal to. And then the last thing I could say is, okay, maybe X is less than or equal to the value of Y, right? Because remember, what we're doing when we're doing inequalities is we are comparing the values of these things, right? And just by the way, these are the symbols that we use for each of these corresponding terms. And sort of a little trick is you could think of this like an arrowhead, and the mouth of the arrow points to the bigger one. What I'll give you all now is just sort of a practical example to bring the concept home, right? So let's say you go, oh geez. Okay, this is supposed to be a car, right? So let's say you're going for your driver's license. They will tell you the minimum age you need to be to apply is 17. So what does that mean? It means the possible ages that you could apply for your driver's license is at 17. You could do 18, 19, 20, and so forth and so forth, right? So there's a range of values that make that statement true. And that is the idea behind solving inequalities. So that's the next thing we want to talk about. We want to talk about what it means to solve an inequality, right? The first thing that we are going to look at, the first type is linear inequality. So I just said, if I want to solve an inequality, it means that I want to find a range of values that would make a statement true. So let's look at an example, practical example. I'm going to buy some apples. I have $10 to spend on apples, right? And each apple costs $2. So what is the possible number of apples that I could buy? Well, our unknown quantity, which is the number of apples times the cost, cannot exceed $10. So this looks very similar to an equation, and we could do a similar set of steps to solve an equation on an inequality to solve an inequality. So So let's see if we were to try to solve this. We want to solve for A. We want to isolate A. So if 2A is less than or equal to 10, then A must be less than or equal to 5. That's it. That is the range of values of A that could satisfy it. So it means I could buy, right? I could buy one apple, I could buy two apples, I could buy three apples, I could buy four, or I could buy five apples. And this is what we are doing when we are solving inequalities. We are finding the range of values that make the statement true. So if you substitute any one of these values into this equation, it is true, right? So just to look at that really quickly here on the side, if we take 3, 2 times 3, which is equal to 6, that is less than or equal to 10. 2 times 5, which is equal to 10, that is 10 is equal to 10, so that is why we use the less than or equal to, right? So that is what we're doing when we're saying that we're going to solve an inequality. So let's look at another example now. Is less than 8, right? So how do we do this? Just like when you're solving an equation, you want to isolate x. So if 2x minus 6 is less than 8, 2x is less than 14, x is less than 7. So if we look at this on a number line, we could say that the possible values of x, which would make this statement true, is when x is less than 7, or maybe x is 2, maybe x is 5, maybe x is 1, maybe x is 0, -1, -2, the other numbers that I just didn't draw on the number line. But dot, dot, dot. They didn't specify what kind of number x is, so maybe it's a rational number, maybe it's 3.5. All those values of x work to make that statement true, right? So you look at another example. Let's say we have, now this time, we have a lower bound, which is 7, and an upper bound, which is 28. So we are going to treat these like two separate inequalities. But what that really means is whatever I do to the left side, I must also do to the right side. So let's expand the bracket, right? So we want to isolate x, right? We solve in fact. Nice. So I could add 7 to all the sides of this thing here. So I could get 14 on this left side, 7x in the middle, and 35 on the right side. And then I could divide throughout by 7 to isolate. So I could get that x is more than 2, but less than or equal to 5, right? So we've just isolated the value of x. So in other words, we've solved for x. And that is exactly what we need to do when we try to solve our inequality. So the range of values of x which satisfy this inequality is between 2 and 5. When we have x is more than 2, we don't include the value of 2, so we use our open circle. And then when we have x is less than or equal to 5, we want to include the value, so we use a closed circle. So just in terms of how we represent the solution, we could use our set builder notation, right? So the values of x such that x is more than 2, but less than or equal to 5. Or we could use interval notation, which kind of describes what this number line is saying. So let's say x is in the interval 2, 5. We use this regular bracket when we don't want to include the number, and we use a square bracket when we want to include the number, right? So this is the interval solution. Right? So x belongs to this interval. And this is, of course, the set builder notation, right? And that is how you will solve a linear inequality. So the next type of inequality that we want to solve is a quadratic inequality, right? So let's look at this example. We have x squared minus 3x minus 18 is greater than 0. What does it mean to solve this inequality? It means we need the values of x which make that statement true. Now, there's something we need to be careful of when we are dealing with nonlinear inequalities. You see, nonlinear equations and nonlinear inequalities by extension are typically represented by a curve. And the thing is, this value here, maybe we could call that value y. That value, depending on the value of x, is either above the x-axis, which is greater than 0, or under the x-axis, which is less than 0. So what is going on here? This green region here is the values of x, which make y less than 0. And this purple region here is the values of x, which make y greater than 0. So to solve this inequality, we need to find the purple region, because that is the region that makes y greater than 0. Or in other words, that is the region that has the values of x, which make this statement true. So how do we find this region? There are 2 points we need to look for. And of course, we know these are called the critical values of the equation. Right? So these 2 points here are the critical values. And the first thing we need to do is identify those critical values. When we identify those critical values, we can determine what regions of x are going to satisfy that inequality. So let me write out some steps here for you. Right? First thing we want to do, we want to identify critical values. So what we need to do is take the equation that is associated with this inequality, which is also called the boundary equation, and we need to solve that equation. And this will give the turning points to the critical values of the equation. Right, so let's do that. So we have x squared minus 3x minus 18 is equal to 0, right? Because that is the equation. And to solve that, we factorize. We could do 6 and 3 plus 3 minus 6. Nice. So when x is equal to minus 3 and x is equal to 6, we have a change in sign for y, right? So those are the critical values. So this value here is actually minus 3. This one is 6. Nice. So now that we have the critical values, the next thing we need to do is step 2. You need to identify your desired region. So what you typically do at this step is this is where you draw your graph to represent the inequality, right? And then you choose which region that you need. So the region we need is the purple region, and that occurs when x is less than minus 3 or x is more than 6. The third step, you could write the solution interval. Right, so based on your graph up here, we need x's less than minus 3 or x's greater than 6. So if we wanted to use set builder notation, our solution is the values of x, where x is less than minus 3 or x is greater than 6. Your solution interval, right? So there's any value less than minus 3 and any value greater than 6. So that's why we put the infinity there, right? So x belongs to this interval here. Okay, so in this next example, we are going to try to solve the inequality x minus 1 times 3x minus 2 is less than x squared. So let's rewrite this and make it look like a quadratic. So we're going to expand the bracket. We have x times 3x, that is 3x squared, minus 3x minus 2x, that's minus 5x, and then plus 2 is less than x squared. Bring over the x squared, we have 2x squared minus 5x plus 2 is less than 0. Nice. What is our first step? We need to identify critical values. So how do we do that? We solve the associated equation. So we are solving the equation 2x squared minus 5x plus 2 is equal to 0. We factorize. Let's see here, we could do 2x, we could do x, 2, 1, minus, minus, right? The critical values are x is a half and x is 2. Nice, we have our critical value. What is the next step? Next step, find desired region. So how do we do that? The best way to do that, I think, is if we sketch the graph. Let's just sketch this graph here. Right, so it cuts at a half and it cuts at 2. Y-axis, x-axis, put a half there, put a 2 there. Now, what is the desired region? We need to solve this equation when it is less than 0. So less than 0 puts us under the x-axis, right? That's when y is less than 0. So we can see here, x is actually between a half and 2. These are the values of x that are going to make that statement, that original inequality, true. Nice. So what's the last step? Step 3. Write our solution interval. So the solution is x belongs to the interval. We are bounded by a half and 2. We don't include it, so a half, 2. And this is our answer. So the next type of inequality we're going to look at is those that involve the absolute value. So just a quick refresher, the absolute value, sometimes you might also hear the modulus effect, is defined as x, and x is greater than or equal to 0, or minus x, and x is less than 0. And on a graph, that would look like this. So what the absolute value function does is it basically measures distance from 0, right? So let's say we have this number line here, right? So let's say we want to find the absolute value of 2. What that means is, what is the distance between 2 and 0 on this number line? Well, it is 2. Now let's find the absolute value of minus 2. So what is the distance between minus 2 and 0? Is 1, 2 units, right? So the absolute value function always outputs a positive number, right? And that is why we define it like this in terms of a piecewise function. So let's look at an example. So using the definition, we could split this up into a piecewise function, right? And it will be x minus 3 when x minus 3 is greater than or equal to 0, or minus x minus 3 when x minus 3 is less than 0. And of course, in each one of these ranges, we could solve for x. We could see that we are going to have 2 cases to deal with. So case number 1, when x is greater than or equal to 3, what do we have going on? Well, we use this top part of the piecewise. So we have x minus 3 is less than 2. So x is less than 5. So in this first case, we get that the range of values of x satisfying this is x must be less than 5. Right? So let's look at case 2. When x is less than 3. Right? So now we use this bottom inequality. So we have minus x minus 3 is less than 2. So we could multiply 3 out by minus 1. So we get x minus 3. We have to flip the sign greater than minus 2. And just side note, why do we do this? Because let's say we had minus x is less than 2. Then we could bring the minus x over and we could bring the 2 over. We'll have minus 2 is less than x. Or in other words, x is greater than minus 2. So what we really did here is we multiply throughout by minus 1 and we flip the sign. So anytime you multiply or divide by a negative sign, you must flip the inequality sign. Right. So let's see what this contribution will be. This will be x is greater than minus 2 plus 3 is 1. Right. So from case 1, we have x is less than 5, and from case 2, we have x is greater than 1. So therefore, the solution is x belongs to the interval 1, 5. And that is your answer. So what I want to show you all now is sort of a shortcut to do this type of inequality, right? Basically, we have two cases. We have x minus 3 is less than 2, and we have x minus 3 is greater than minus 2. So if we wanted to remove the absolute value sign or the modular sign, we could think about it like this. We could say if x minus 3 is less than 2, so this is sort of an alternative way to do it, then minus 2 is less than x minus 3, which is less than 2. Right? And we could isolate x, so we add 3 to all sides, so we get minus 2 plus 3 is 1, less than x is less than 5, which is the open interval 1, 5. So this is another way we could do these types of inequalities. So let's look at another example now. X minus 1 is greater than 0. So what are we trying to find here? Let's look at this on the number line. Remember, the absolute value gives us our distance from 0. So the only way this distance here could be greater than 0 is if x minus 1 is not 0. Or in other words, if x is not 1, right? Because any value of x except for 1 is going to make this statement true. So let's try it. Let's try minus 2. We have the absolute value of minus 2 minus 1, which is equal to the absolute value of minus 3, which is 3, is greater than 0. Let's try 1.5. 1.5 minus 1 is 0.5 is 0.5, which is greater than 0. The only value where this fails is when x is 1. Right? So if we need to find a distance that is greater or less than 0, we need to exclude the value, which makes this thing here 0. And that value is x is equal to 1. So our solution is the open interval minus infinity 1 union 1 infinity. And that is our answer for this one. Okay, so this next example, we have two absolute value functions in the inequality. So even though at first it might look a little overwhelming, all we're going to do is stick to our definitions, right? So let's start with the outermost absolute value. So we know that the absolute value of 2x minus absolute x minus 1 is equal to 2x minus absolute value of x minus 1 when 2x minus the absolute value of x minus 1 is greater than or equal to 0. And the second case is minus 2x minus the absolute value of x minus 1 when 2x minus the absolute value of x minus 1 is less than 0. So it is obviously tricky to find the exact value of x over here, right? So let's see what's going on. We have either this first case, so either 2x minus the absolute value of x minus 1 is greater than 3, or minus 2x minus absolute x minus 1 is greater than 3. So let's make the absolute value of x minus 1 the subject, right? So minus absolute x minus 1 is greater than 3 minus 2x, or 2x minus absolute x minus 1. We flip the signs, less than minus 3. Right, let's go down here. Absolute value of x minus 1, flip the sign, minus 3 plus 2x, or minus x minus 1 less than minus 3 minus 2x. And then let's just neaten this up a little bit. Yeah, we could put 2x minus 3, or x minus 1. We flip the sign again, 3 plus 2x. Nice. So now we can take cases, right? Because let's go back to our definition on this absolute value. So we have the absolute value of x minus 1 is x minus 1 when x minus 1 is greater than or equal to 0, and minus x minus 1 when x minus 1 is less than 0. So this gives x is greater than or equal to 1, and this gives x is less than 1. So now it is easy to look at the two cases with specific values of x, right? So over here, it was kind of hard to find the specific value of x to break it into cases. But down here with the inner inequality, the inner absolute value, we can find it, right? So let's look at case 1. When x is greater than or equal to 1. What do we have going on here? So when x is greater than or equal to 1, we use the top part of the piecewise function, right? So we get x minus 1 is less than 2x minus 3, or x minus 1 is greater than 3 plus 2x, right? And then this is very straightforward. This is a linear inequality. So we have minus 1 plus 3 is less than 2x minus x, or the minus 1 minus 3 is greater than 2x minus x. I just group in the x's on one side. So this gives 2 is less than x, or minus 4 is greater than x. But look at this. What is the condition for this case? X must be, x must be greater than or equal to 1. So if x must be greater than or equal to 1, how could minus 4 be greater than x? This case here is given a contradiction, which means the only valid contribution for the possible values of x is right here. So from case 1, we have x is greater than 2. So case 2 is when x is less than 1. So now we use the bottom part of the piecewise over here, right? So we have minus x minus 1. So minus x minus 1 is less than 2x minus 3, or minus x minus 1 is greater than 3 plus 2x. Let's see what contributions we have here now. Right, so again, linear inequality, minus sign. So we flip the signs. X minus 1 is greater than minus 2x plus 3, or x minus 1 is less than minus 3 minus 2x. So we could bring the x's over here. So we have 3x is greater than 4, or 3x is less than minus 2. Right, and in this case, x is greater than 4 over 3, or x is less than minus 2 over 3. We have another contradiction. Why? Because x is less than 1. The condition for this case is that x must be less than 1. So having x is greater than 4/3 or 1 and a third, that is a contradiction. We don't have a contribution from that component there. The only contribution to the solution comes from here. We have x is less than minus 2 over 3. So when we split it into cases, we saw that x is either greater than 2 or it is less than minus 2 over 3. So the solution is x is less than minus 2 over 3 or x is greater than 2. If we use our interval notation, we'll have x belongs to minus infinity, minus 2 over 3. This is our open interval, union the open interval to infinity. And that is your answer there. So our next type of inequalities are rational inequalities. And these inequalities, of course, contain rational expression. And that is nothing but a function in x divided by another function in x. So in the context of inequalities, we essentially have two major cases to focus on, right? Our expression p of x over q of x could be less than 0, or p of x over q of x could be greater than 0. If you have less than or equal to or greater than or equal to, all you need to include is the values of x, which make the statement equal to 0. And you're good to go. So in general, we're looking at these two cases. So how could we have these statements being true? Let's look at this first one. The first way that this could be true is if p of x is less than 0 and q of x is greater than 0. Right, so I'll just use numbers as an example. Let's say the numerator is less than 0, so like minus 1, and the denominator is greater than 0, so 2. This number here, minus 1/2, is less than 0. Right? What is the second way? The second way is if p of x is greater than 0 and q of x is less than 0. Right? So for example, let's say we had 3 divided by minus 5. Minus 3/5 is, of course, less than 0. Right? So that is how this expression could be less than 0. Let's see now how the expression could be more than 0. So the first way is if p of x is greater than 0 and q of x is also greater than 0. Right? So let's say we have 2 over 3. This is, of course, greater than 0. The second way is if p of x is less than 0 and q of x is also less than 0. Right? Let's say we had like minus 1 divided by minus 4. That is equal to 1 over 4, which is, of course, greater than 0. So these things here we're going to use to solve rational inequalities. And I'll show you how now with this example. So let's say we want to solve the inequality x cubed over x squared plus 1 is less than 0. In the quadratic inequalities, what we did was found the critical points because those were the points where there would have been a change in sign. And we looked at what was necessary for us to get the solution reached out. So why can't we do that here? Well, technically we could, but it is a bit difficult because if you look at the graph of this inequality or the graph of the function x cubed over x squared plus 1, it looks something like that. And that is not exactly something that we could just sketch easily. With quadratics, it is easy to sketch a curve. But with these rational numbers, it's not so straightforward, right? So that is why we're going to rely on our rules here. Right. So this inequality is less than 0. So we are looking at one of these two cases here. Either the numerator is less than 0 and the denominator is greater, or vice versa. So let's look at this denominator actually. Notice x squared is greater than or equal to 0 for all real values of x. So x squared plus 1 is definitely greater than 0 for all real values of x, meaning the denominator is positive. So for this statement to be true, the numerator has to be negative. So to solve this inequality, the values of x, which makes this entire inequality negative, are the same values of x. I'm just going to put 3 equal sign, which make x cubed less than 0, right? So our solution, we could just take the cube roots on both sides, is actually x is less than 0. And you could try this. You could substitute any number less than 0, and this expression here will be less than 0, right? So in this next example, we want to solve this inequality. But the rules that we discussed before works when the inequality is in one of these two forms. So to solve this, I'm going to write some steps for you all. Step 1, the first thing that we need to do is write the inequality in the form p of x divided by q of x. And in this question, it's greater than 0, right? So to do that, we can bring everything over. We have x over x minus 2 minus 1 over x plus 1 is greater than 0. So we already have the greater than 0 on the right side. So now to simplify this, we just find the LCM. It'll be x minus 2 times x plus 1. That's the LCM. And then this will be x into x plus 1 minus x minus 2, greater than 0. So we could just expand the numerator now, right? So x times x is x squared, plus x minus x is 0, minus times minus 2 is plus 2, greater than 0. Nice. So this is now of the form p of x over q of x is greater than 0. So what we need to do now is we need to see which case that we are dealing with here. Maybe I'll write step 2, determine whether numerator and the denominator is greater than 0 or less than 0, positive or negative, right? So what do we have here? Just like the previous example, x squared is greater than or equal to 0 for all real values of x. So x squared plus 2 is definitely greater than 0. That is for sure a true statement. So in this case, our numerator is greater than 0. So if our numerator is greater than 0, how do we get this expression greater than 0? Well, the denominator must also be greater than 0. So what we need to find, the solution is the same as the set of values of x such that the denominator is greater than 0. Right? Maybe I could write step 3. Find corresponding values of x. Right? So this is a quadratic, and we know how to solve a quadratic inequality. Really quickly, we could sketch our graph. Right? It will cut at -1 and 2. This is -1, this is 2. And it is greater than 0, so we need this region here, positive. So the solution is going to be minus infinity, -1, union to infinity. And that is the answer for this question here. So this next example incorporates rational inequalities and the absolute value, right? So if we want to solve this inequality, we recall our definition. We have the absolute value of x minus 2 over x plus 4. Using our definition, we can split it up into piecewise. We have x minus 2 over x plus 4 when x minus 2 over x plus 4 is greater than or equal to 0. And we have minus x minus 2 over x plus 4 when x minus 2 over x plus 4 is less than 0. So at this point, to split up into cases, we are not too concerned with the exact value of x. So let's just take the first case to be the top value and the second case to be the bottom value, right? So we have case 1. That is x minus 2 over x plus 4 is greater than 3. Now, to solve this, you may be tempted to cross multiply, right? But we're not going to do that. And the reason we're not going to do that is because we want to write this in the form P of x over Q of x is greater than 0. So in order to do that, we need to bring everything to one side. We will have x minus 2 over x plus 4 minus 3 is greater than 0. All right, so our LCM is x plus 4. We have x minus 2 minus 3 into x plus 4 is greater than 0. When we expand this, we are left with x minus 3x is minus 2x. And then minus 2 minus 12 is minus 14, where x plus 4 is greater than 0. We could divide throughout by minus 2 over, let's factor it out, x plus 7 over x plus 4 greater than 0. And now we divide throughout x plus 7 over x plus 4, flip the sign, 0, right? That minus 2 is our constant, right? So we could divide that out and make things easier for us. So how do we solve an inequality that looks like this? You see, we can't really tell if the numerator or denominator is going to be greater than or less than 0 because we don't know the value of x. And x is any real number. So what we're going to do is actually convert this into a quadratic. I'm just going to put a side note. Convert in quotation because you're not really converting it, but into quadratic. But just for the sake of your remembering what we need to do, we're going to multiply throughout by the denominator squared. And why do we multiply by the denominator squared and not just the denominator? Because we don't want to lose the critical value. So when we do that, we get x plus 7 times x plus 4 is less than 0. So of course, we know how to solve quadratic inequalities. So let's give a quick sketch. It's going to cut at minus 7 and minus 4, right? So it will look something like that. Just a sketch. Right. It is less than 0. We want this region here. So the contribution for this part, or this case, is x is going to belong to the open interval minus 7, minus 4. Nice. So let's move on to case 2 now. So that is when we use this bottom part of the piecewise function. So we have case 2 minus x minus 2 over x plus 4. So we could divide throughout by the negative sign. We'll have x minus 2 over x plus 4 is less than minus 3. We want to do the same thing, write it in our known form. So we're going to have x minus 2 over x plus 4 plus 3 is less than 0. We simplify this. X plus 4, x minus 2 plus 3 times x plus 4 is less than 0. We expand the numerator. We're going to get x plus 3x is 4x minus 2 plus 12 is plus 10 over x plus 4 is less than 0. If we want, we could divide throughout by 2. So we're left with 2x plus 5 over x plus 4 less than 0. There's no change in sign. Now we need to multiply throughout by the denominator squared, so we don't lose the critical value. We have 2x plus 5 times x plus 4 is less than 0. So, of course, by now, you should be more than comfortable solving something like this. All right, so let's just sketch it out there. This should be minus 4. This will be minus 2.5, or minus 512. Right, we want less than 0, so that is this region here underneath the x-axis. And we have y next. So the solution contribution here is that x belongs to the open interval minus 4 minus 5 on 2. So if we combine our answers from case 1 and case 2, our solution is minus 7 minus 4 union minus 4 minus 5 over 2. That is our answer. So the last type of inequalities that we want to go over are those proof type questions that you would have seen on your assignment and tutorial sheet, right? And there are basically two methods that I'll give you all to approach these types of questions. And for this first one, this first example, we're going to use a direct proof to show our result, right? So for a direct proof, we know we need to take something that we know to be true and show our result, right? So I just want to kind of make a side note here for you all to see something. Because we're dealing with greater than or equal to, I'm going to take a statement that I know is always greater than or equal to 0. So you could consider this statement here, right? This is, of course, true because any number squared is greater than or equal to 0. So this thing here is non-negative. So if we expand it, we'll have a squared minus 2ab plus b squared is greater than or equal to 0. Therefore, a squared plus b squared is greater than or equal to 2ab, right? So let's go ahead with the proof now, right? So you can already see why I chose this fact to do the proof, because we could see that we're kind of working towards something that looks like this. But the catch here is we don't have a squared and b squared, we have x and y. So if we take a squared, so I'll just write here, if we let a squared equal x and b squared equal y, then a is the square root of x and b is the square root of y. So for this proof, I'm going to take, so for the proof, I'm going to take root x minus root y squared, which we know is greater than or equal to 0, implies that x minus 2 root x root y plus y greater than or equal to 0 right? Which implies that x plus y is greater than or equal to 2 root x root y, which implies x plus y over 2 is greater than or equal to root x root y. And of course, root x root y is the same as the square root of xy. And then I could square both sides to get x plus y over 2 squared is greater than or equal to x, y, which is exactly the result that we needed to show. So what we did here is we take a known fact and we use the direct method of proof to get our result. So in this next example, we want to prove this statement. So how do we go about doing that? You see, because again, we have this greater than or equal to sign, we typically want to lead towards something that we are squaring, because that is a sure thing that we know is greater than or equal to 0. So let's write this as u fort minus u squared v plus v squared is greater than or equal to 0. And what you might notice is that this looks really similar to a squared minus 2ab plus b squared is greater than or equal to 0, or a minus b squared is greater than or equal to 0, which we of course know is true, right? So what our goal is going to be is to manipulate this statement here and try to find a way to express it as a perfect square. So what that means is you can kind of see here that u fort is a squared, right? So a is going to be u squared. We want to find u squared minus kv squared is greater than or equal to 0, right? So let's expand this. This is u fort minus 2k u squared v plus k squared v squared. So if we compare our two expressions here, let's call this 2, and let's call this. So if we compare equation 1 and 2, and especially if we focus in on the middle terms, we could see that 2k is equal to 1, so k is equal to a half. So let's expand this now with k being a half. We're going to get u fort minus u squared v plus 1/4 v squared is greater than or equal to 0. But look at this. This looks almost identical to equation 1. The only difference is the coefficient of v squared. You see, if we were to write instead u fort minus u squared v plus 1/4 v squared plus 3/4 v squared, we have our original expression, u fort minus u squared v plus v squared. And we just showed that it was greater than or equal to 0, right? So if we formalize this proof now, so I'm going to do a proof by contradiction for this one. So assume, for sake of contradiction, that u fort plus v squared is less than u squared v. Then u fort plus v squared minus u squared v is less than 0. And that implies that u squared minus a half v squared plus 3/4 v squared is less than 0. But u squared minus a half v squared is greater than or equal to 0, and v squared is greater than or equal to 0, which implies 3/4 b squared is greater than or equal to 0. Hence, u squared minus a half v squared plus 3/4 v squared greater than or equal to 0, which contradicts our assumption that u fort plus v squared is less than u squared v. Hence, u fort plus v squared must be greater than or equal to u squared v. And that is our proof by contradiction. Of course, if you wanted to do a direct proof, kind of justifying using the green writing here, then that's fine as well. But I just wanted to show you all an alternative method on how to do that, right? So the big thing here, especially when you're dealing with greater than or equal to 0, you want to find a way to write your expression as a square or a sum of squares or a sum of positive two. And that is why we did this entire reasoning here, right? So that is it for inequalities. Hopefully this video helps. As always, if you have any questions, you could email me or message on the group chat. Okay, bye.